Can you accurately drill into something that you can't see? Surgeons can, but to do so they rely on very advanced surgical navigation technology. It turns out, though, that we can mimic that technology using simple consumer VR hardware. During spinal surgery, instruments like drills and screwdrivers are tracked with infrared cameras, so their positions can be displayed relative to radiographic imaging. Unlike surgical instruments, which are tracked using infrared retroreflectors, this system relies on active electronics coupled to the device in order to track the location of it in the real world and display its coordinates on screen. Another tracker is attached to a block of wood with a bolt. That way, we can track the position of the objects based on the position of the trackers. This enables translation of real-world positions into VR space, which are then rendered on screen. But how are the trackers tracked? Here, I'm using Valve's Lighthouse tracking system, which sweeps infrared beams across the room. These beams are detected by IR sensors on HTC Vive trackers. Given the known positions of the sensors on the trackers and the known characteristics of the Lighthouse's beam sweep, the exact orientation and position of the trackers are determined using Valve's Steam VR software, Triad Semi's OpenVR Python wrapper, and some custom code. The tracked VR positions are then rendered on screen. But how do we relate the position of the tracker to the position of the object that we actually care about? Here, there are two approaches that are used. In the first approach, the physical object is scanned using an iPhone LiDAR scanner. In Blender, the model is cleaned up and its origin is set to where the tracker attaches. This creates a textured 3D model that is accurate enough to use with navigation. For the drill and other instruments, though, we take a different approach. Rather than risking the large 3D model of the drill blocking line of sight to the target, we instead focus on the tip of the drill bit, which is the most important part to visualize relative to the target you're drilling into. To determine the relationship between the tip of the drill bit and the tracker, the tip of the drill bit is put at a fixed point and the rest of the drill is rotated and moved while software records the position of the tracker. Because the tip is stationary while everything else moves, the software can calculate exactly where the tip is relative to the tracker. Now that we have the locations of the objects tracked and visual representations of them, we have everything that we need to actually navigate. Here, the drill is touching marked locations on the wood in the real world, which is accurately reflected in the visualized model. But to better mimic minimally invasive surgery, we can cover the wood and leave the tracker sticking out. Then, we can navigate to these intersections and drill into the wood by looking at the screen. When we reveal the hole, we can see that we were able to navigate accurately using the tracked system and drill into the wood. But this system is inspired by spinal surgical navigation, so its real test comes down to whether or not it can accurately drill into a model of a spine. Like the block of wood, this model was scanned and a tracker is attached to it using a bolt. The trajectory for the drill is planned using a green cylinder, and the model is split up into parts to make it easier to visualize the trajectory later. We are then able to carefully navigate the tip of the drill bit to the pedicle, ensure the trajectories are aligned, and then carefully drill into the pedicle. Finally, we can drive a screw into the pilot hole that we just made. So there you have it, surgical spinal navigation mimicked using consumer VR hardware. However, you might have noticed that when I was drilling the third hole into the block of wood, the tip of the drill bit slipped on the fabric and entered about 3 millimeters off from where I intended. In addition, when I was drilling into the pedicle, the tip of the drill slipped on the curved surface. In both instances, although the location of the drill bit's tip was correctly visualized, that doesn't guarantee where it ends up. To solve for that problem, we'll need to apply a different set of technology. But we'll save that for another video.